Hey everyone, how's it going? It is day 17 of the Advent of Code in Ruby Daily Coding Challenge. We are on a streak and we're keeping it alive. So let's get right into it. If you've been around here so far, you know that Advent of Code is a 25 daily challenge that happens every year, and I'm doing this on stream so that I actually have motivation to keep it up and not get distracted by work and life obligations and just keep on it. So we're just keeping it going. So far, we're en route to our vacation, and apparently breaking various international laws to get on the plane and to uh, get get it going, hacking systems as we go along. So we are in a morally dubious state. Uh, so what is today's problem? Well, it has something to do with Conway cubes. That's all I know because we're going in blind. As your flight slowly drifts sky, the elves at the Mythical Information Bureau at the North Pole contact you. They'd like some help debugging a malfunctioning experimental energy source aboard one of their super secret imaging satellites. The experimental energy source is based on cutting edge technology, a set of Conway cubes contained in a pocket dimension. When you hear it's having problems, you can't help but agree to take a look. Pocket dimension contains an infinite three-dimensional grid. At every integer uh, three-dimensional coordinate, there exists a single cube which is either active or inactive. Okay, so like x, y, and z I guess can be infinite then? That's what it sounds like. In the initial state of the pocket demonstration, almost all of the cubes start as inactive. The only exception to this is a small flat region of cubes. And that's going to be the only exception is a small flat region of cubes. That's our puzzle input. Cubes in this region start at the specified active. Let me start that again. The cubes in this region start in the specified active, hash, or inactive stop state. The energy source then proceeds to boot up by executing 6 cycles. Each cube only ever considers its neighbors. Any of the 26 other cubes where any of their coordinates differ at most by 1. Okay, so anything that's if you're like if you're like 1111, or I guess 111, there's only 3 coordinates, right? You care about 000, you care about 001, 011, 111, and all the permutations. So we might actually be borrowing from like a few days ago when we figured out permutations um, for some other problem. I don't remember exactly the problem, but we did something with permutations. So there's probably code that we can steal there, maybe, possibly. Figure out all the neighbors. Each cube only, okay. Each cube only considers its neighbors. So, for example, given the cube 1, 2, 3, the neighbors include. Okay, so they went through the same exercise I did. During a cycle, all cubes simultaneously change their state according to the following rules. If a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active. Otherwise, the cube then becomes inactive. If a cube is inactive, okay. If a cube is inactive but exactly 3 of its neighbors are active, the cube becomes active. Okay. Otherwise, the cube remains inactive. Okay. If two of three neighbor, two of th if 2 of 3 cube neighbors are active around an active cube, it stays on. Otherwise, it turns off. It needs 2 or 3 to stay alive. If the cube is inactive but 3 of its neighbors are active, it turns on another cube. Otherwise, it remains inactive. So it sounds like it sounds the energy probably expands or contracts, but doesn't stay the same. Okay. The engineers responsible for this experimental energy source would like you to simulate the pocket dimension and determine what the configuration of cubes should be at the end of a 6-cycle process. Consider the following state. We have a simple input. Even though the pocket dimension is 3-dimensional, this initial state represents a small 2-dimensional slice of it. In particular, oh right, we're in 3 dimensions. That makes everything complicated, doesn't it? In particular, this initial state defines a 3x3x1 region of the 3-dimensional space. Okay. But if we do have the assumption that 3 surrounding have to turn on, exactly 2 or 3. Okay, so for this guy is inactive. Let's actually just kind of like walk through Notepad first and see what this looks like reasonably before we let them tell us the answer. So initially this guy has only one active neighbor. So it's inactive, but exactly 3, then it turns active, otherwise it stays inactive. Okay, that makes sense. This guy is active and has only one active number. So if it's active and it doesn't have 2 or 3 active, then it goes inactive. Guy here is inactive and it has 2 active running it. So that turns off, that stays off. This guy here has 3 surrounding it, actives around it, and it's inactive, so we light it up. This guy here has more than 3 active surrounding it, so it stays inactive. Okay. Guy is active and has 1, 2, 3 active around it, so that stays lit. For this guy here, it only has 1 active, right? It only has 1 active surrounding it, so it turns off. Guy here has 3 actives surrounding it, so it turns on. And this has 2 actives surrounding it, so it stays on. So this is iteration 1. Why does this one turn on? After 1 cycle, simulate a few cycles of the initial state following configurations where the flow of each cycle is shown layer by layer at each given parenthesis. I don't see why this would be turned on. The initial state of the pocket dimension, almost all cubes start active. The only exception, all flat regional cubes. Your cubes in this region start as a specified active X and active state. After a full 6-cycle boot process completes, 112 cubes are left in the active state. So if we do assume that they're correct here, which they probably are, and there's probably some part of the definition that I'm confusing here. Why is this expanding? Block dimension exists by three-dimensional grid. At every enter position there exists. I'm trying to think if like this is actually supposed to be like puzzling, but might make it more clear. So if we assume that I'm wondering if like this is actually a 3x3 grid, 3x3x3, and I'm just seeing one slice and that the slices are duplicated. Oh, everything is inactive. Didn't it say everything is inactive except for the slice I have? The initial state of the pocket dimension, almost all cubes start inactive. The only exception is a small flat region of cubes, Europe, but the cubes in this region start with the specified active or inactive flags. The energy source proceeds to boot up, executing 6 cycles. Cube only neighbors. Only considers its neighbor. Example given the cube bad. That all makes sense. So a cube is active. Exactly 2 or 3 of its neighbors are also active. Cube bad. I think I'm also not sure like which part of the 3D slice, like if which Z is this at? I don't really understand why they're saying Z equals -1 here. cycles. Five. Okay, so the z is actually infinite, right? Every number in any direction is going to be disabled. This is still only surrounded by 1. Cube is active if cube is inactive, but exactly three of its neighbors are active. The cube becomes active. This is the only one that's active on it. I don't... This should still be inactive. There's no world where that should be active. Maybe if I run it through a program, and maybe that does make more sense somehow. I don't know. Just write a quick program that gives does the rules as written and run with it, I guess. We're gonna make a simple input. Not what we wanted to draw. It selected too much. Okay. Much of this we don't need from last time. Get rid of. Maybe I'm just like incredibly dumb, and this actually does work algorithmically the way it does. Start off by having input sample here. Everything on the name. Okay, so we're going to say that in going to be indexed. I keep my brain straight on this. Actually, the outer array is going to be the z. Y is up, down, so actually, yeah, so it's byx is how this is going to be indexed. Returns same structure, but bigger every. But wait, after the first one, it didn't expand though. So for main, what we're going to just do. Well, this test doesn't make sense to me. We're going to make everything arrays all the way through rather than mess with like the string to array conversion. Because enumerable will sometimes work and sometimes won't. We need to like do each on each, right? So let's just pre-print our cube initially. A problem. Okay, so this looks accurate. This matches this structure here. We might need a nice way to print these out, though. Actually, no. Just to give us some visibility into. I want to call it Z here. Kind of like. Let's not worry about that quite yet. So slices each row. Print cube. Print cube. See what this looks like. So that's what we would expect to have. So let's expand our cube now. So we don't want to be clobbering. Value add y z cube xyz. Maybe this will actually be I think that's actually valid. I think we just assume that anything that's outside bounds has to be 0, right? Has to be like a unset. It's kind of like weird to do the math in my head for this, just because the structure of the cube is expanding each time we do this, right? Except not happening the first time, I guess. No, I guess it is. What are we ultimately for the number of active members? It doesn't really matter. If we're expanding or not. Like, it's already infinite. I guess the first thing we do I guess we make a bigger cube. Is less than oh x oh. It's interesting. I'm actually just thinking through this now, and I'm realizing this also could be um, a series of bit fields also because we're talking about ons and offs. But I don't think that bit field arithmetic makes sense. I think that that actually makes it complicated, so I'm not gonna go too far down that rabbit hole. It's just kind of frustrating to think through. What if I was allowed to have negative values? Then we're not talking about an array anymore, we're talking about a hash table. That might... There might be value there. Because then I don't really need to worry about... If we have like a three-dimensional hash table, we can have negative index. Not a big deal. Yeah, that's what we're doing. That's what we're doing. That actually makes so much more sense. Let's do that. Okay, so let's change... Cube is now an associative array. It actually makes life so much easier, I think, here. Lines map. We're just each with an X. Ooh. I think we want the line is still Y. Index. And we'll start off initializing this as because our Z is going to be 0. We can make those hashes or as hashes for now. And we just leave it sparse if it's not. So this changes. Print cube changes a bit here. So the cube max z is max. Can actually wrap this up a little bit. We don't even worry about allocating until we actually need it to expand. So max each do the index. So slice equals. We kind of need like the printing it is a little more complicated. Printing is a little more complicated. I think we can all agree on that. We can assume that. We can come together on that. We want these to be consistently sized, so this is going to be all the slices, the cube values, right? So a slice has an array of strings, like an array of one-character strings. A minute of that might be interesting. Seems a little wasteful. It's all getting kind of like weird and complicated, actually. We can actually break these out into maybe their own functions, I think. My min, cube. Well, we can actually do this for everything. Z min, cube. Because I think we're going to need this for other stuff too, because we're going to need it for iteration as well. So the z index min is really easy. Cube is min. Z max, literally the same thing. Max. Y min, cube. Values. Map. Keys. Latin min. That seems pretty reasonable. Latin max. Okay, so now for X min. Cube. Values. Map. Values, right? These are all arrays. No, they're not arrays anymore. They're hashes as well, right? I guess if there's like nothing ever in the leftmost column, it doesn't really matter for that to be 0, I guess. That's a little weird, but I think that's correct. Okay, max there. So we can just do zmin up to zmax. We need to do that for the cube. Cube. X cube. Each do y. Then x min. X max cube. Each do x. Print. So now we do something. Cube. If Now we do value at. Cube e y and cube e x. We're gonna return the hashy hash. Else it's a dot. So if cube x of okay, so we'll just print out value. YZ. We'll add a new line there. So I think this is probably gonna crash and burn, right? Don't you? Yeah, we definitely crash and burned. Yeah, 100%. Oh wait, no. We did it bad. We overread it. We overwrit it. And it wasn't into that. Value add. We have value add. Oh, did I do why did I do the weird casing here? I don't know why I keep on doing this. The casing's always very bad. That's not what we're going for here either. This is we have 3x3, which is can actually do here instead, I guess. We actually don't need to calculate min-max for Z. Got a thick new line there. That no. D cube or no? Cube. 0 equals 0. Here's what y min and what y max. Actually, let's just do all the maxes, right? We went to array somewhere here. Went array. 0, 1, 2. Okay, so we do have 3x3. That's good, right? Oh, this is where this is where we were really dumb. Once we can short circuit this, so that's fine. Our value at was just really bad. So that looks like our input. So we can get rid of all this. And now we can start expanding the cube. We can actually start doing the very first thing that this problem calls for. Let's see here. Say cube equals is a hash table, right? That's pretty cool. That's pretty exciting. Okay, so let me think here. I think if we're like indexing based off of all the values, or the based on the values of the old cube, or based on the values of. I think that there's always the potential. There's always the potential that we could be up to -1 away from where we were initially. So I think we can make this part a little better. Now I'm thinking. Kind of have that hard-coded 0 concept, which is not great. We can have a set value at, right? Cube x, y, z. Unless cube e c cube. I guess that's actually more of a cube z or equals a hash cube z y or equals hash cube z y x equals x equals value, right? Value is always hash, so we don't need to actually add configuration for that. So we can actually set value at cube x idx, y idx, 0. That might be a little nicer. See if that blows up anything. I might have had half completed code. Might expand. Yeah. That's not what we want. Let's do that again. That matches our original. We're happy with that. Okay, so now that we have this value set at, which will aggressively kind of like allocate hashes as we need to, we can have our expand not really care about the what exists already and just worry about what is now. You can just look at the values we have and work from there. New cube does need to be a hash still. Start off. Then the cube is max do slice. Or no, each doozy. So let me actually, I think that just combinations. Zero. One, two. And then to an array. Now it's permutation. Okay, so that's not what we want actually. We want I guess actually to be more realistic with our example, minus 1, 1. We want something that's going to return 8. We had something with permutations before. Repeated permutation. Okay, that's what we were looking for. One. That's 1. Okay, this is what we're looking for. Perfect. So for each of these, we're going to have a repeated permutation. Do the X, Y, and Z for each of these. So we kind of like take a peek, one north, one east, one south, one west, one up, one down each time. But anyway, we do need to get through each of these first, though. Cube Z. We know that Z is a valid thing. Z is min. This approach, I wonder if this approach actually doesn't work because we potentially need disabled things that are before that, I guess. That are before the offset. Huh. Because, like, suppose if this was, instead of this, suppose that this was a period, right? In our example, there would be no zero index. If there's no zero index, though, like, the -1 index is not going to be ever relevant because these are all 0. Because at most it could be one above and one below, and we need to care about exactly. It would still be hit by like things that are turned on. You have to be adjacent to things turned on for this to be relevant. If you're not adjacent to anything that's turned on, then it's not relevant. And we're going to be looking at adjacent things. So this approach is actually 100% fine now that I'm thinking. Just had a little brain thing. Okay, so now that we're in here, now that we have our X, Y, and Z, let's on our top level create the permutation so we don't need to be constantly creating. (1) -1. Have repeated permutation tray. Let's shrink this down so we have a little. If this first approach doesn't work, I'm probably just going to turn off stream and try to talk to friends and see where I'm misunderstanding the problem, because the fact that I was running it through hand and it wasn't doing what I expected it to do makes me think I may just not understand the problem at all.
No, it's not. There's no use for me to grind against instructions I don't understand. So, getting some clarity is going to be more productive for everyone. Let's see here. We have our offsets. Offset set. What am I trying to do here? We can actually break this out into a separate thing, I think. So let's hand wave that a little bit for a second and implement that. XYZ. We only need to create the offsets once. So let's, or that as a variable, so we're not creating it repeatedly. I don't think it's valuable to do that. So it doesn't really matter which one we say is X, Y, and Z in the 0, 1, 2. 0, 1, minus 1. That part doesn't matter. We're just going to have an array of 3-element arrays that, and each one covers a different scenario. We can actually do this, making the enabled our hash pounds. If we find something, it's 1. If not, it's 0. And we sum them up. Let's actually just do some printing with this idea. And just see, like, XYZ. But I just kind of like want to see all these counts and see if what I'm doing makes sense. I didn't actually expand the cube, so that's why we didn't have any output there. That makes a lot of sense. That. Okay, we did something wrong. Expand. Let's just do expand. Yeah, it's just expand. This is all Z0. That makes sense. Enable adjacent is 27. That makes no sense whatsoever. This is just gibberish. I'm glad that we went through this. Also very weird that this would go. Just all very confusing. X, Y, Z. Not yet. Not accurate. Because we print out value at the cube, and it doesn't do that weird thing. Am I doing some sort of like a signs instead of equal? No, that doesn't even make sense. Oh, we're doing XYZ. That's not actually correct here. That's why. We were doing it very wrong. Y and Y offset. Search Z. Z and Z offset. Search X. Search Y. Search Z. Value equal. X. Y. Z. Value. And now we just do line here. And we value equals pound. I don't think we even need the debugging statement at this point because I think found the issue for sure. Okay, that's a lot better. So let's get rid of this here. And see what all these look like. So I think we do need to do y min, y max actually for here instead of just looking at the values. And burned. in cube. Y max cube. If we're doing that, we probably should do that same here. Max. Because I think we might be like skipping things that we need to care about. Because it's possible, for example, okay, we need to actually test this top left. We need to test 0, 0, 0, right? We always have to test 0, 0, 0 because, I mean, that's a valid part of this grid already. An alternative that we can do is we can have a mix of periods and pounds and not just periods throughout this, and just have it treat blank as a period. That might actually end up being simpler. Okay, so adjacent 1, that makes a whole lot of sense. One has adjacent 2. I don't know why that is exactly. I think my brain's just kind of gravy right now, and I'm not really making any headway here, so I think I might just kind of hold this for tomorrow, because my brain's not really grokking this. I appreciate you guys all hanging on, but I think that we just need to cut the cord. I'll be back tomorrow, once I've had a little more sleep to deal with this, I think. We'll do some catch up. Catch y'all later, guys.